If we stop and consider what truly defines, advanced human intelligence, our greatest cognitive superpower, it isn't just speed or memory.
Right.
It's rapid adaptation. We are constantly dropped into novel, unfamiliar contexts, whether that means moving to a new city, trying to figure out a complex new app, or learning the unspoken rules of a new job. And we manage to thrive.
That ability to pivot it's essential.
Wow.
And cognitive science suggests this profound, flexible adaptability is tied directly to one core mechanism: the efficient construction and dynamic refinement of internal representations of the environment.
The world model.
The world model. If you want to understand how a system, human or AI, makes sense of the world, you have to look at its world model. That model encapsulates everything from object dynamics to causal structure.
But if these world models are so central, why do current powerful AI systems often feel so rigid? They can beat the world champion at Go, but you introduce one tiny new rule and the whole thing just breaks.
Well, the central problem is that most current AI world models are built on static training. They focus on predicting the next event based on observing massive data sets, like predicting the next frame of a video.
That's all offline observation.
It is. Human learning, however, happens through active interaction in a new, unfamiliar domain.
So our mission today is to dive deep into that divergence. We're focusing on what researchers call world model induction, the mechanism where a system efficiently learns and builds its understanding on the fly just by, playing and experimenting.
And this capacity for rapid induction is absolutely critical if we ever hope to achieve true artificial general intelligence.
Okay, let's unpack the blueprint for human adaptation. The research points toward this beautiful mechanism for achieving incredibly sample-efficient learning. What does cognitive science tell us about how we structure our knowledge?
Well, the mechanism is often described using a hierarchical structure. Essentially, we don't just have one big world model. We have layers of knowledge that sort of talk to each other.
Layers. Can you walk us through those?
Absolutely. Think of it as two primary categories. At the bottom layer, you have the instance world model.
Okay.
This is the highly detailed, domain-specific, knowledge-constructed ad hoc. Imagine you move to a new town. This is the mental map of your specific street, where the potholes are, which local shop opens earliest.
Super granular knowledge for just that one place.
Exactly.
So what sits above that? What makes our learning so fast when we move to a different town?
That's the key. Above the instance model, you have the abstract world models. These are the generalizable concepts and universal principles. For example, your innate understanding of real-world physics or intuitive psychology, the idea that other people have goals.
And that applies everywhere.
Universally.
So if I move from, say, New York to London, I don't have to relearn gravity, even though the street map is entirely new. I just plug in the new local traffic rules.
Exactly. And that's the source of sample efficiency. The abstract models provide incredibly powerful priors.
And by priors, you just mean strong pre-existing assumptions.
A perfect way to put it. Strong beliefs that allow you to construct that new specific instance model with minimal interaction. You only need a few minutes of exposure to figure out the new town's traffic flow because you already understand mass and momentum. You don't start from zero.
That strong starting assumption is vital. But the research also emphasizes that human learning isn't passive observation, which unfortunately is still the AI norm. We function more like the child as scientist. What does that mean in practical terms?
It means our learning is hypothesis-driven exploration. We don't just wait for data, we actively design these little experiments through our actions.
I could like that.
So if you encounter a new object in a game, you don't randomly push buttons. You test specific hypotheses. Does this object roll? Or does pushing the green button make the door open?
You're intentionally generating the most informative observation you can.
Precisely. We plan actions specifically to discriminate between competing ideas about the environment's underlying rules. We are planning to learn, and this active, targeted strategy is how humans converge on an accurate representation of a new domain with minimal, highly efficient interaction.
And this rapid induction capability is what underpins everything AGI needs to have. Rapid learning, robust generalization, and cross-domain transfer.
Absolutely. If an AI can't efficiently build these models, it will be limited to just optimization within known constraints. The real world doesn't operate that way.
Here's where the conversation about evaluating AI gets really interesting. Because if traditional benchmarks, those static fixed environments like specific versions of chess or Atari-only test optimization,
Yeah.
what does the new evaluation framework even look like?
The new standard is centered on novel games. And this is more than just increasing the difficulty. These games must contain genuine, deep, and continually refreshing novelty in their underlying game
So
structures.
the rules, the physics, the objectives, they're all unknown or shifting.
Exactly. They force the AI to construct a brand new world model from scratch, not just reuse an old one.
That sounds incredibly difficult to design systematically. What are the key requirements for a game to truly measure induction?
The sources outline three core desiderata. The first one is pretty clear: novelty in game structures. We need environments that test all three levels of generalization we just discussed.
Okay, so give us an example for testing rapid learning.
For rapid learning, the underlying mechanics have to be hidden, requiring inference through active exploration. A great example is the abstraction and reasoning corpus, or ARC-AGI3.
I've seen those. They're like little logic puzzles.
They are. You're given an input and output grid, and you have to deduce the simple hidden rule that transforms one to the other. There are no instructions. You only learn by experimenting.
And to test robust generalization, how do you make an environment that forces continuous updating?
The rules themselves have to evolve over time. Imagine a game where gravity suddenly reverses, or where jumping changes depending on your character's color. The agent has to continuously monitor the environment for shifts, forcing it to update its model.
Like real life.
Just like real life, where laws or technology are always changing.
And the pinnacle, testing cross-domain generalization. That's where those high-level abstract models really shine.
Absolutely. Here, we transfer abstract principles. So if an agent has induced an intuitive physics model in one game, we can test it with something like the virtual tools game.
What's that?
The agent has to select a tool, say a lever or a ramp, to get a red ball into a green bin. It's never seen this specific tool or setup before, but it succeeds by leveraging general physics knowledge about force, leverage, and trajectory.
Now for the second requirement.
Hmm.
The games must be intuitive and learnable for human players. Why is using human intuition as a baseline so critical?
Well, if the task is just arbitrarily complex or depends on some weird non-physical logic, we aren't really measuring human-like adaptation. The goal is to measure skills that resonate with our own inductive biases, the cognitive shortcuts that let us learn quickly.
So if a person can figure it out in a few minutes, an AI should show similar efficiency.
Exactly. If the game is too alien, we lose the whole point of comparison.
And the third requirement focuses on diversity.
Right. We need diversity in world models and learning mechanisms. The test suite has to force the AI to build different kinds of internal representations, not just models of physical objects, but sophisticated mental models of other agents.
What cognitive scientists call theory of mind.
Theory of mind, yes, especially in multi-agent games. And diversity in how they learn, sometimes through pure interaction, other times by using language instructions or just watching another agent.
I find the concept of the benchmark itself being a dynamic generative process fascinating. Because once a powerful AI system masters these novel games, they're not novel anymore.
That's right. The field recognized that fixed benchmarks inevitably lead to overfitting. So the best approach is to create a generative system that continually creates new games by systematically altering the rules or mechanics. It's a renewable source of true novelty.
Okay, moving on to evaluation. It's not enough to just measure if the AI wins. If we're assessing induction, we need to see how the AI learns. What metrics assess the model building process itself?
We need a comprehensive framework that probes the internal models, not just the final outcome. The first metric, and arguably the most important, is sample efficiency in adaptation.
Meaning we restrict the learning budget, put them on the clock.
Exactly. Researchers run case studies where they plot the success rate as a function of the number of learning samples the agent uses. By restricting that budget, we can directly compare human efficiency, who might solve a puzzle in 4 attempts, versus the model's efficiency.
It really reveals how quickly the agent converges on the right model.
It does.
The second critical area is the qualitative analysis of exploration. How do you measure the quality of an agent's curiosity?
You analyze the agent's behavior. You look for its strategy for gathering information. What we're looking for is evidence of targeted, efficient exploration behavior that shows the agent has identified a knowledge gap and is performing actions to test a specific hypothesis.
And what's the contrast? What does poor exploration look like?
Poor or diffuse exploration is what you see in older, purely reactive models like DDQN. These models often display less directed, sometimes random movements because they lack a coherent internal model. They aren't planning to learn, they're just flailing to see what happens.
Targeted exploration is the signature of a system that's actively building a world model.
Precisely.
And finally, how do we look inside the black box? I mean, how do we probe the internal models of these massive neural networks to confirm the AI truly understands the principles it inferred?
That's the million-dollar question. For systems that use explicit programs, the inferred rules might be directly visible. But for massive neural architectures like LLMs, it's harder.
That's where the targeted questions come in, right?
Yes. A very promising technique is to use natural language to ask targeted questions about abstract principles or game-specific properties.
Like asking a language model if it understands object permanence or the specific mass of a new block, even if it hasn't been directly trained on that property.
Precisely. If the model can answer accurately, it suggests the internal representation truly encodes the underlying causal principles, rather than just having learned a successful sequence of actions. It's a powerful way to get a glimpse inside.
So, if we step back, the push for novel games is clearly a critical evolutionary step. It moves AI from systems optimized for fixed performance to flexible, human-like adaptability.
It does.
And that's essential for creating AI scientists or collaborative systems that need to function in the messy, dynamic real world.
It forces us to raise the standard of intelligence measurement. But this whole pursuit also raises some fundamental questions that are still very much open. The first is about necessity. Is this complex, hierarchical structure truly necessary for human-level adaptation?
I can imagine some skeptics arguing that maybe a purely reactive system, if it's just massive enough, could still achieve surprising adaptation simply through incredible pattern generalization.
Right. Bypassing the need for an explicit internal world model altogether.
Yeah.
That perspective exists, but the research points to sample efficiency being the critical test. The extent to which model-free approaches can achieve human-level sample-efficient adaptation remains a massive, open, empirical question. This new framework is designed to help answer that.
And the final challenge, external validity. We are demonstrating rapid adaptation in these controlled game environments, but how well do those capabilities actually transfer to the continuous complexity of the real world?
That link is what needs rigorous assessment next. While games are powerful tools, we have to ensure that the progress we make on these controlled benchmarks truly translates into meaningful, trustworthy, and flexible AI capabilities when these systems are deployed in the complex world we actually live in. That translation is the next frontier.